Good morning, everyone. Welcome to the lecture series for plant modeling. Today, we'll be starting module 5 that deals with leaf energy balance. Leaf energy balance is a very important concept in understanding how leaves and in turn plants will manage temperature as well as the water balance related to it. So it is mainly through various processes like absorption of energy, transmission of energy. So transmission of energy means light energy, heat energy, emission of energy, and also reflectance of energy. So we'll be going into detail into how the energy is managed in plants, which is key to regulating temperature and processes that are related to temperature. So we learned how photosynthesis is very much related to temperature. So by knowing how the plants or the leaf plants at the leaf scale manage temperature and manage energy, we'll be getting more insight into how this is going to impact photosynthesis.
So, what is basically energy balance? When we had talked about water, particularly when I had talked about the Likert measurements, I hope I'm audible to everyone. Can someone just confirm? Yeah, okay. So, thank you. So, when we were talking about how a Likert measures photosynthetic rate and transpiration rate, we had done some calculations or we had looked into some equations that were considering what is the total mass of the mass of carbon dioxide in the initial condition and what is it in the final condition when a leaf is kept in a chamber and the leaf takes in carbon dioxide. So in the end, the output would have some carbon dioxide less. And the equations were formed based on the mass balance concept. Basically, whatever is going in will be equal to whatever is coming out plus the storage. Similar to that, energy also follows the same rule where the total energy that is possessed by a system is equal to whatever energy goes in is going to come out as is whatever energy goes in will also be equal to the energy that is coming out of the system. And if there is anything less, that would be probable because some of that energy is stored in the system. So energy balance in general terms is nothing but the energy input will be equal to the energy output plus the storage of the energy in that system where energy can be in any ways. It can be the energy from the sun, it can be energy because of heat, it can be chemical energy, mechanical energy, electrical energy, any sort of energy. It is applicable to any sort of energy. And energy out can be, say, we are in terms of photosynthesis, we learned that first the energy of light is taken up by the plants, which is then converted into chemical energy in the form of ATP and NADPH. And then ATP and NADPH is then utilized for the Calvin cycle and photosynthetic process. So the energy that is coming in is basically the solar radiation, and the energy to which it is getting converted is the chemical energy. That chemical energy is further again utilized for the manufacture of uh, carbohydrates. And the carbohydrates will result in the growth of the plant, and that energy that is stored, that energy that is utilized for the manufacture of carbon dioxide is stored in the form of the biomass in the plant, and a lot of energy is released out back into the system in the form of heat. So that is what is happening when it comes to a plant. Now, if we go into the basics of energy, it is again the capacity that is required for a particular work to be done. So there are various forms of energy. Like I said, kinetic energy is the energy possessed by a moving body. Potential energy is the energy that is possessed by a body with respect to its position or when it is static. Then there's solar energy, chemical energy, and all sorts of all forms of energy. And energy is usually expressed in units of joules. It is also express in terms of horsepower or kilowatt hour or calories. We say when it comes to eating food and our health, we account for the calories of food that we eat, the kilocalories or calories that are burned out, which is a measure of how much energy we take in and how much energy is removed from our system. Then electrovolts is also one unit of energy, which is basically the energy possessed by particles. So this is just a depiction of how there are different forms of energy which can result in a lot of work being done. Mechanical energy can make us move. The nuclear energy can result in nuclear fission reaction. Chemical energy is used by plants, and electrical energy is used for lighting up power lines, and electromagnetic energy is used in the form of radio waves, microwaves, and everything. Now, as far as a plant is concerned, in order to determine, say, let's consider a leaf, not a whole plant. If you're considering a leaf, the energy balance determines how much energy is absorbed by the plant, utilized by the plant, and then lost as heat. So the incoming energy is removed from the system, or it exits the system in the form of heat, and the sum of the energy that goes inside is equal to the heat that is lost out plus whatever energy is stored in the plant when the products of photosynthesis are generated. Like in biomass, it is stored. While photosynthesis is happening, that energy is staying in the system. So those small amounts of energy is the energy that is stored in the leaf, and energy that leaves the leaf is going to be heat, and energy that is received by the energy that is entering the leaf is going to be the sun's energy. Now, when we talk about the sun's energy, calling it as the sun's energy is a very broad term that explains the sun's energy. Now, if you look at sun's energy, okay, let's just look at what are the incoming energies. We have the solar radiation, which can also be called as a shortwave radiation. So, when we talk about solar radiations in a general term, it means shortwave radiation, and we'll go into what is shortwave and what is longwave radiations. Again, along with shortwave radiations, there are longwave radiations from the from the surroundings. Then the outgoing energy is going to be the radiative heat loss, the sensible heat loss, and the latent heat loss via transpiration. And the stored energy is going to be the energy that is used during photosynthesis and the heat that is stored in the leaf tissues, basically to regulate the leaf temperature. So some amount of heat needs to be retained in the leaves so that it maintains a certain amount of temperature, because plants at very high temperature is going to get destroyed, and at very low temperature also nothing is going to function. So it has to store an amount of energy so that the temperature is regulated or temperature is maintained in the leaf, and this is the energy that is being stored in the system, which is the leaf. Now let us look into each of these terms and what they exactly are and how we can um, use it from the daily available data that we have. So radiation is nothing but the energy that is traveling in space in the form of particles or waves. So solar radiation, when we say, is the sun's energy in the form of particles or sun's energy in the form of electromagnetic waves. So we know this electromagnetic spectrum that is starting from the gamma rays and ending up to the radio waves. And if you see the wavelength of the electromagnetic spectrum, which is starting at gamma rays, is very small. You can see that it starts, gamma rays is up to some 0.01 nanometers. After that, X-rays come, which is 10 nanometers, and it goes on until radio waves, microwaves of 30 nanometer, 30 millimeter. Now, nanometer is 10 to the power minus 9 meter, and here it comes to millimeter, which is 10 to the power minus 3 meter. So you can also see that these waves that is in the range of far infrared microwaves and radio waves are all long wavelength, while the starting ones have short wavelengths because the value of the wavelength is smaller. So shortwave radiations are nothing but that portion of the electromagnetic spectrum which has a relatively shorter wavelength and higher energy. So one speciality of the short wavelength radiations are or electromagnetic waves are that they are high in energy and it is coming from the sun. As we know, all of these components of the electromagnetic spectrum are coming from the sun only, and it has different wavelengths, and these different wavelengths, the ones which are coming in the short wavelength are the short wave radiations, what we call as short wave radiations. As far as a plant is concerned, a plant can take in or plant utilizes majorly three kind of shortwave radiations, which are the ultraviolet radiations, which start at around 100. These are not exact values, but approximately it the 100 nanometer to 400 nanometer range of values in the ultraviolet spectrum is utilized by plants. Similarly, visible light, we all know, from 400 to 700 nanometers, especially the blue and red lights are taken up by the plants. And then near infrared radiation that is extending up to 700 to around 3000 nanometer is utilized by plants. So somewhere in the middle from here and from here, the electromagnetic spectrum is useful to plants from ultraviolet radiations spanning from this value till near infrared radiations. Not the it is not making use of the entire infrared radiation spectrum, but near infrared radiation that is extending up to 3000 nanometers. In the same way, what is long wave radiation? It is nothing but again the radiations that is coming in the portion of the electromagnetic system that has higher wavelength. And this higher wavelength radiations are going to have relatively lower energy. And the radiations that is of importance to us, or the electromagnetic spectrum which is important to us in with respect to the utilization level of plants, is something around 4000 to 30,000 nanometers. That is again until maybe this portion, not all of the infrared portion, but till 30,000 nanometers, the far infrared or the far infrared that is having a bit higher wavelength than the ones in the shortwave radiation range is what is useful to plants. Now, this these far infrared radiations are generally called as thermal radiation, so thermal energy, which is mostly obtained when Earth's surface is heated up and they emit these thermal radiations. Then atmosphere is heated up, they emit these thermal radiation. Clouds are heated up, they emit this thermal radiation. So the shortwave radiations are often in the form of direct sunlight or diffuse sunlight. That is, sunlight is coming, it is reflected by or it is scattered by some particles, and it will go off, and those shortwave radiations are obtained in that form. Whereas this thermal radiation is obtained from Earth's surface. That is, when the sunlight heats up the Earth's surface, it emits some radiation which comes under this range of far infrared portion. So as far as plants are concerned, we talked about how visible light, the spectrum from 400 to 700 nanometer is of the most useful to the plant. The blue color and the red color part of the spectrum, and infrared radiation, the energy that is obtained from the surroundings, that is the energy that is emitted by the Earth's surface or from the cloud or from the atmosphere, is what is the radiations in the infrared portion. And ultraviolet radiation is mostly harmful to plants in large amount, but in small amounts it is plants do make use of UV radiation. Now, when we talk about sun's radiation for estimations or for plants which are at and leaves, where we are analyzing the processes at a very molecular level, we call the sun's radiation as plant available radiation. Basically, whatever radiation is actively utilized by the plant is called plant available radiation, and or photosynthetically active radiation, which is basically because light is what is used in photosynthesis mostly. So photosynthesis is a process that is making use of this light energy uh, to the maximum extent. So photosynthetically active radiation is the radiation, sun's radiation, that is effectively utilized by the plants, and it is falling in between this 400 to 700 nanometer wavelength. So we said that infrared radiation and UV radiation is also utilized by the plant, but let's now focus on this photosynthetically active radiation, which is the radiation levels that are utilized during the process of photosynthesis, lying in the visible lights range, which is 400 to 700 nanometers. Now, in order to make use of the solar radiation, uh, we usually get the solar radiation in the form of weather data in terms of watts per meter square, or in terms of joules per meter square per day. But when we need to utilize it, or when we need to analyze data for the purposes of estimations in photosynthesis in plants, we have to convert this energy into the photon flux density of this radiation, and this is called photosynthetic photon flux density. So photosynthetic photon flux density is measuring how many photons or how many light particles are hitting the leaf every second. So if you remember, when we had generated the AQ curves, the x-axis was ppft, which is photosynthetic photon flux density, and the unit was in micromoles of photons per meter square per second. And the y-axis was in, again, micromoles of carbon dioxide per meter square per second. So uh, when we are when we are utilizing the sun's radiation to estimate photosynthesis, so study any photosynthetically related process, we have to convert that into micromoles of photons per meter square per second, which is nothing but the photon flux density. So photon is the tiny particle of light. Flux is the number of photons that is moving across a unit area. And density is how concentrated these photons are in that particular area. Now, 1 micromole of photons, because our unit of interest is micromoles of photons per meter square per day, 1 micromole of photons is equal to 6.022 into 10 to the power 17 photons. So, it is saying that just like how 18 grams are present in 1 mole of water, here there are 6.022 into 10 to the power 17 photons in Y when you consider 1 micromole of photons. So like I said, how do we convert this to PPFT? How do we convert the usually available solar radiation data to PPFT is what we look into right now. So solar energy or solar radiation data is generally available in units of watt per meter square or megajoules per meter square per day. And we know the relation between watt and joules. 1 watt is equal to 1 joule per second. So joule is the watt is the unit of power. So energy per hour is, or energy per unit time is giving us power. So 1 watt is equal to 1 joule per second. So 1 watt per meter square will be 1 joule per meter square per second. Now, in order to convert the solar radiation data to PPFT, the first step that we require to do is to assume what portion of the visible light spectrum is absorbed by plants. So when a total amount of solar radiation is available to plants, it is assumed that only 40 to 80 percentage of the solar radiation is taken up by plants. When I say solar radiation, I'm talking about the shortwave radiations. So when light, particularly in the visible light spectrum. So when visible light is available to plants, it doesn't take up the entire visible energy that is available to it. Instead, it only takes around 40 to 80% of the light, the solar shortwave radiation that is available to it. So first if we have the data, we will only consider half of that data. If we have 200 watt per meter square as the data available to us, then we will only consider around 45 to 50% of the data for estimation. So here say it's 200, then we take only 100 watt per meter square. Now, energy of one photon is given by this Planck's equation, which is nothing but the Planck's constant into velocity of light divided by the wavelength of light. So this is the Planck's equation where the energy of particles, the energy of one photon is given, which is equal to hc by lambda. H is the Planck's constant. It is 6.63 into 10 to the power minus 34 joule second. Velocity of light, we know 3 into 10 to the power 8 meter per second. And wavelength is in the units of meter. And finally, we get the energy of one photon in units of joules. So if we substitute these two values in this equation, we get that one photon has E joules of energy, then one mole of photons will have E into Na joules of energy. So now we got the energy of one photon, which is given by this Planck's equation. Now our intention is to find what is the energy of one mole of photon, because we want to convert it into micromoles per meter square per second. So definitely we are looking for what is the energy possessed by a mole of photons. And this is given by multiplying this energy of one photon with something called the Avogadro's number, which has a value of 6.022 into 10 to the power 23. So it is important that yeah. So 6.022 into 10 to the power 23 is the Avogadro's number, and it is in units of per mole, that is photons per mole. So this many number of photons are there in one mole. So earlier I had talked about the same number in terms of micromole. So that is why this number is coming down to 10 to the power 70. So Avogadro's number is the number of photons per mole of photon, and it is 6.022 into 10 to the power 23. So if one mole contains this many number of photons, and the energy of one photon is equal to hc by lambda, we can all substitute these values in here to get 6.63 into 10 to the power minus 34. This is not 10 minus 34, it is 10 to the power minus 34. Let me just make that correction. Okay, so when we substitute the Avogadro's number, the Planck's constant, and the velocity of light in this equation, we get that the energy of a mole of photon is going to be 0.1198 by lambda. Now we don't know lambda because it is a spectrum, 400 to 700 nanometers. So it can be either 400 or 450 or 500 or 550, any of it. So we keep this as lambda itself, but we have the values of all other constants in this equation. The Avogadro's number, we have the Planck's constant, we have the velocity of light. So when we substitute and we find out the final answer, we get it as 0.1198 by lambda joules per mole. So one photon is having this many hc by lambda joules of energy. Then one mole of photons will have 0.1198 by lambda joules per mole of energy. Now, this is still in the unit of joules and moles. So how do we convert this to micromoles per meter square per second? So in order to convert it to micromoles per meter square per second, we had initially looked at 1 watt per meter square is equal to 1 joule per meter square per second. So ppfd will be equal to this solar energy divided by the energy of 1 mole of photons. So if 1 mole of photons possess 0.1198 by lambda joules per mole, then 1 watt per meter square or 1 joule per meter square per second is going to have the same amount of energy divided by the energy of 1 mole of photons. And then we will get this value when 1 divided by 0.1198 is 8.347 lambda moles per meter square per second. Since we need it in micromoles per meter square per second, we get 8.347 into 10 to the power 6 micromoles per meter square per second. Now here, if you look at the units, this 1 watt per meter square is nothing but 1 joule per meter square per second. So these this joule and joule cancels. So this mole will come on the top and it will become moles per meter square per second. So this is how we get the final equation in terms of, or final energy in terms of moles per meter square per second. And in order to convert it to micromoles, I have just added a 10 to the power 6, which will convert it into micromoles per meter square per second. So basically 1 watt per meter square is equal to 8.347 into 10 to the power 6 lambda micromoles of meter square per second, where the unit of lambda, you need to be very careful, is going to be in meters, not in nanometers. It is going to be in meters. So lambda will be in meters, and and then when you substitute this lambda value, which should be in meters, into this equation, you will get you can convert the solar radiation data into micromoles of photons per meter square per second. So based on this, I have a small problem that you can do that will help you remember this equation. So I need you to convert 1000 watt per meter square into ppfd for a light radiation of wavelength 550 nanometer. So the equation, uh, 1000 watt per meter square is the solar radiation, and the wavelength of the equation is 550 nanometer. Using this last equation over here, this one circled in red, please find out what is the energy in micromoles of photons per meter square per second. I'll be just moving ahead once I get one or two answers, so please try to do it. Very simple question. You just have to substitute the um, the wavelength. You have the equation for 1 watt per meter square. So we'll find out for 1000 by substituting the value of lambda as 550 nanometers in terms of meter. If is anybody else doing, or shall I move on to the solution? Okay, I don't seem to be getting any response, so I'll just move on to the solution. So I had said that initially around 50 percentage of the light that is coming from the solar radiation is what should be considered for the estimation of the incoming for the PPFD. So since it is 1000, we need to only consider 500 watt per meter square for the estimation. Then, since 1 watt per meter square is this value, 1000 will be, of course, 500 will be 500 into this 8.37 in 347 into 10 to the power 6 into lambda. Now, lambda has been given in terms of nanometers. It is important that you substitute it in terms of meters. So it will become into 10 to the power minus 9 meters. And when you do all this calculation together, you will get 22,095. Yeah, around 2,300 micromoles per meter square per second. So if you noticed in the AQ curves also, we are having the light range going from 500 to something around 2,500 and all in the AQ curve. So this will be generally the values that you get in micromoles per meter square per second should be coming to around 500. It's not a thumb rule or anything, but if you say if you're getting very less values, then you might have to go back to your calculation and check if the calculation is right. So values of solar radiation generally, when converted to PPFP, will have to give some values in the range of 500 to say 3000 or something. So this is how you will do the conversion for of solar radiation. Um, that you get in terms of watt per meter square or joules per meter square per second into ppft. So I hope this part is clear to all of you. Now like I said, two types of radiations are entering the leaves. One is the shortwave radiation and one is the long wave radiation. The shortwave radiation is what we talked about now. The solar radiation, when anybody says solar radiation, they actually mean the shortwave radiations, because the long wave radiations are the radiations that are emitted by the surroundings, by the clouds, and not by the sun directly. So that is why shortwave radiation is what is being talked about when anybody says solar radiation. Now, shortwave radiation is in the form of direct sunlight, skylight, and reflected light, whereas long wave radiation is in the form of the ones emitted by atmosphere, clouds, surface of the ground, by nearby plants, and all other objects are the energy or the radiation that is emitted by all of these objects apart from the sun is what is called as a long wave radiation. Now, in shortwave radiation, around 40 to 80 percentage of the light is taken up by the plants, whereas in long wave radiation, around 96 percentage of the light is taken up by the plants. Now, why is it that plants are taking up so much more long wave radiation in comparison to short wave radiation? Is because these plants they behave like black bodies, nearly like almost like black bodies. So black bodies are those bodies that absorb all of the uh, light, and in the same way plants also behave that way. So as a result it absorbs all the incident thermal radiation, and in the same way it will also emit the same levels of thermal radiation that it is capable of absorbing. Now we know this black body radiation or black body uh, and then why is this thermal radiation being taken up by the plant is to redistribute this radiation to maintain the temperature of the plant. So even when it is cold or during the night time when there is no solar radiation, the temperature is regulated by this long wave radiation that is emitted or absorbed by the plant. So it is for this that long wave radiations are extensively absorbed and emitted. It is not only absorbing, but it is also at the same rate emitting these long wave radiations. Now, the amount of radiation that is emitted by a leaf is proportional to the fourth power of its temperature in Kelvin. Now, this equation we are all familiar. It is a black body equation for black body radiation, where this is the emissivity factor. This is the Stephen Boltzmann's constant, and this is the temperature. Now, so we have moved on from solar radiation that is incoming to radiation that is outgoing from the leaf. Now, long wave radiations are also taken up by the leaf, but what is the amount of long wave radiation that is taken up and emitted by the leaf is given by this equation, which is the equation, Stephen Boltzmann's black body equation given by the uh, black body phenomenon. So we talked about solar radiation and the long wave radiation from the surrounding, and now we are going to talk about how is this long wave radiation, what amount of long wave radiation is emitted by the system. Now, emitted by the system is this radiation, which is again in terms of watt per meter square, emissivity of the surface. Sigma is the Stephen Boltzmann's constant, which has a value of 5.67 into 10 to the power minus 8 watt per meter square per Kelvin. And TL, not just TL is the temperature of the leaf. So, the radiation that is emitted by a leaf is proportional to the fourth power of its temperature. And the emissivity of this leaf, this epsilon value is going to extend in the range of 0.8 to 0.98. So if a body absorbs all of the light, then the emissivity factor is going to be 1. Epsilon is going to be 1. And if it reflects all of the light, like say take a mirror, the emissivity of a mirror will be 0. Emissivity of a perfect black body will be 1. And leaves have emissivity ranging between 0.8 and around 0.98. So emissivity is measuring how efficiently an object can emit thermal radiation. Now we are not talking about any solar or sun's or light energy here. This is all thermal or heat energy that is being emitted by the body. If you see this picture over here, we see that sun direct energy is there, diffuse radiation is there. The long wave input is also there. That is the same amount of energy is taken up by the plants. Um, taken up by the plants from the surroundings, and it is also released from the plant, emitted from the plants. And this energy that is emitted from the plants is what is a function of the temperature of the leaf. Now, The radiative heat loss from plants during the radiative energy, that is the sum of the energy that is incoming in the short wave radiation, and that is being out that is outgoing as long wave radiation, is positive in the morning time, but during night time it is usually reversed. That is, thermal radiation that is exiting the system will be more, or thermal radiation will be prominent in that situation, obviously, because short wave radiations are not going to be there in nighttime in the absence of sunlight. So thermal radiation is what is going to play a important role during the night time. So now we saw what is one of the components of energy that is exiting the system, which is the radiative heat loss, or nothing but the long wave radiation that is being emitted by the plant. Now, another energy that is emitted by the plant, or heat that is thrown out of plant or released by the plant, is sensible heat loss. So, what is sensible heat loss? Now, when you heat an object, the temperature of the object rises. So, if you keep a cooking vessel, a steel vessel on a stove, and you light the stove, the temperature of that body is going to change. Similarly, if you cool that object, again the temperature of that body is going to change. This phenomenon where there is a temperature change when heat is supplied to a body is called the sensible heat. So sensible heat is the heat that is resulting in a temperature change in a body. So in order to for sensible heat to occur, the body has sensible heat can occur in two ways. Either you can keep the body in touch with a hot object. Say, suppose you keep an ice. No, let's leave ice. You keep, yeah, you pour water in a hot vessel. Then heat is going to be transferred from that vessel to the water. So there has to be some kind of contact between bodies of two temperature. Then this heat will be transferred, and this process of heat transfer is called heat transfer by conduction. So we know sensible heat is the heat that is resulting in a change in temperature. It can occur in two ways, by conduction or convection. Conduction is nothing but direct any transfer that is occurring as a result of direct contact. So if you pour low temperature water into a high temperature vessel, the heat will be transferred from the higher temperature to the lower temperature, which is from the vessel into the water. So in terms of a leaf, the leaf surface is what is in contact with the air. So the leaf, if the leaf is warmer, the temperature, the heat will be transferred from the leaf to the air. In the same way, if the air is warmer, the heat will be transferred from the air to the leaf. So it is going to heat the leaf. Now, another type of sensible heat loss or heat exchange is happening through convection, which is basically heat being transferred as a result of another medium, which is air. So suppose if you have, if say, let's go back to the vessel itself. If the vessel is available and you blow some air into it, some of it will again result in a reduction in temperature. So this heat loss or heat change as a result of moving wind or moving air is called heat transfer by convection. So two types of sensible heat is anything that brings about a difference in the temperature of the object as a result of heating. If the heating is low and the temperature reduces, then that is also called sensible heat. If you add heat to an object, the temperature increases, then that is also called sensible heat. Sensible heat is because we can we can sense that sense the heat as a result of temperature variation. Now, sensible heat lost from leaves is given by this equation, which is a function of the temperature. That is, change in the temperature of the leaf minus change in temperature of the leaf and the air, and the specific heat capacity of the air and the air density divided by something called the boundary layer or diffusion resistance. So this is directly proportional to the change in temperature or the difference in temperature between the two bodies in contact and inversely proportional to the boundary layer resistance, or directly proportional to the boundary layer conductance. We know that resistance is equal to the reciprocal of conductance, but here it is inversely proportional to the resistance of the boundary layer. So let's look into what that is in terms of sensible heat loss for leaves. So just like how we learned about stomatal conductance and boundary layer conductance to water vapor, and stomatal conductance to carbon dioxide, and boundary layer conductance to carbon dioxide, there is also a boundary layer uh, that is existing when heat is being transferred. So when water has to move out from inside the leaf to the air, it has to face the resistance offered by the stomata to the water, and it also has to face the resistance that is offered by the boundary layer to the for the water particles that have reached the surface of the leaf. Same in the condition of carbon dioxide. In case of heat, heat has got nothing to do with the stomata. Stomata is not the one that is dissipating heat. Heat is dissipated from all parts of the plant. Since we're looking into leaf, in case of leaf, heat is dissipated from the leaf, and the leaf has a thin layer of air around it, which is the boundary layer, leaf boundary layer. Now, this thin layer of air is offering resistance to the movement of heat from the leaf to the air. So if you look at it, when a leaf is exposed to air, the leaf is not directly in contact with air, but in turn there is a boundary layer that is existing between the leaf. There's a boundary layer around the leaf, and then you have the air or the atmospheric surrounding situation. And this boundary layer is a function of the smoothness of the leaf, say the size of the leaf, the dimension of the leaf. Now, if you see, if you have a very flat, uh, if you have a very large surface, then the boundary layer is going to be large, because the area that is offering resistance to the heat transfer is going to be more. So more resistance means that boundary layer is going to be higher. In the same way, if the leaf, say if it is a big leaf, one leaf has smooth surface and one leaf has a rough surface because of some hair particles that are seen on the leaf, something called trichomes and all. Then again, the smoother surface will have lesser boundary, and the surface with hairs and trichomes will have a larger boundary layer. So boundary layer is affected by the dimension of the leaf as well as the surface of the leaf. Now, sensible heat loss through conduction has to, cross this boundary layer, which is a function of the smoothness of the leaf and size of the leaf. In the same way, heat loss also happens through convection, that is, which is nothing but the movement of air that is going to result in the heat transfer. Now, even when air is hitting the leaf particle, it is not going to take away all of the heat, because there's a boundary layer existing around the leaf. So when leaf warms the air, some of the air is transferred to the boundary layer by conduction, and this heat that is existing in the boundary layer, air can carry away this heat which is lasting in the boundary layer. So if there is no wind, because of the density of warm air, which is lighter than cold air, it will slowly rise back into the atmosphere. So whatever heat was transferred from the leaf to the boundary layer, if it goes on its own because there is no wind, it is called natural convection, because warm air is lighter than cold air. So warm air has a tendency to rise and cold air will take its place. So this process is natural convection. And if there is a lot of wind, then it is going to push this warm air from the boundary layer and replace it with cool air. So first, the sensible heat loss has to occur where heat has to be transferred from the leaf to the boundary layer. And then from the boundary layer, it is pushed by the air, which is the sensible heat loss through convection. So this is how sensible heat loss is happening in plants. First, there is sensible heat loss by conduction. where heat is transferred from the leaf to the boundary layer. And then there is sensible heat loss through convection, where heat is then transferred by the wind that is blowing, which will move the heat from the boundary layer. So if there is more wind, there will be more dissipation of heat. If the wind is less, heat will be retained in the around the plant, which is going to keep making the plant or the leaf more warmer. So convective heat loss is a function of the wind speed. So more wind, more convection, faster the cooling. Again, this is also a function of the size and shape of the leaves, because smaller and narrow leaves will have smaller boundary layer, and larger leaves or hairy rough surface leaves will have larger boundary layer, which is going to reduce convection because it has to fight the resistance from the boundary layer to a larger extent in comparison to smaller layer. So the uh, convective heat transfer is directly proportional to the wind speed and inversely proportional to the leaf width. That is, if the width of the leaf is big, the boundary layer resistance is going to be more, so heat transfer is going to be less. But if the wind speed is higher, then heat transfer is going to be more. So this is how the convective heat transfer is related. It is a function of. So now we see that sensible heat loss from leaves is nothing but a heat loss that is resulting in the temperature difference of the leaf. So if a leaf is getting heated more and it is resulting in increasing the temperature of the leaf, then it is sensible heat. Again, if the heat is more and some heat is being removed from the system, from the leaf, then it is that is also sensible heat, which is resulting in the temperature loss of it, a change in temperature. Basically, temperature is increasing or decreasing in case of sensible heat. So it is called sensible heat because we can sense it. We can sense it with our with whatever, a thermometer, or by feeling it, because there's a change in temperature. So we looked at what sensible heat loss is. Now what we'll look into is what is latent heat loss. Now we were talking about sensible heat, which is nothing but heat that is resulting in a temperature difference. Now there is also another kind of heat which will result in not in change in temperature, but it will change the phase of the object. Now if you look at ice is the freezing point of ice is at 0 degrees. So until, maybe this will help you in understanding more. So if you see, this is sensible heat. That is because this y-axis, which is temperature, is changing. When a sensible heat is resulting in a change in temperature, whereas latent heat is something where you don't see any change in temperature, but instead what changes is the phase of the object changes. If you're looking at water over here, ice will turn into liquid without any change in temperature. This heat is called the latent heat. So latent heat is the heat that results in the phase change of the object that is experiencing heat without any change in temperature, whereas sensible heat is the heat that is resulting in the change in temperature of the object without any change in the phase. So again, a water which keeps on increasing its temperature until 100 degrees Celsius starts boiling. Now, at this 100 degrees Celsius itself, water, which is in the form of liquid, will change into water vapor without any further increase in temperature. But here, what is changing is the phase of it is changing. It is changing from liquid to gaseous phase. So, this kind of heat that is resulting in the phase change of an object is called the latent heat. In plants, latent heat is experienced or emitted in the form of the energy lost when the water inside the leaf is converted into water vapor and leaves the leaves through the stomata as the process of transpiration. So when transpiration occurs, basically latent heat is emitted or latent heat is lost. Now this will remove the heat. That is why we say when transpiration occurs, it results in cooling of the leaf, which is reducing the temperature of the, which is cooling the leaf. We don't say it is reducing the temperature of the leaf. We say it is cooling the leaf because the heat is removed from the system as a result of water being converted to water vapor and leaving the leaf. Now, just like how sensible heat is a function of the temperature difference, latent heat flux, which is a function of the latent heat of vaporization in terms of transpiration. When we look at transpiration, latent heat flux is given in this form where lambda is the latent heat flux, latent heat of vaporization, and E is the rate of transpiration. Now, latent heat is a function of the temperature of the air. So by using this equation, if you have the temperature of the air, we can get the latent heat of vaporization of water. So it is different for different kinds of temperature. And using this equation called the Penman-Monteith equation, there are a lot of equations through which you can estimate the transpiration, but the most commonly used one and most popularly used one is the Penman-Monteith equation, which is giving this latent heat flux as a function of the vapor pressure deficit, the aerodynamic conductance, slope of the saturation, and so many terms like that. So, in order to estimate the latent heat of vaporization, latent heat energy, we can estimate it using the Penman-Monteith equation. We will just see what are the terms in this Penman-Monteith equation, because this is a relatively large equation. You don't have to memorize it or anything, but this is something good to know. So we see the latent heat flux here, lambda into E, where lambda is the latent heat of vaporization of water, E is the transpiration rate. Now this term del is nothing but the slope of the saturation vapor pressure curve. Now we had looked at the psychrometric chart in our earlier classes. In earlier classes, the psychrometric chart had a curve, that is the curve with the 100% relative humidity. That is called the saturation curve. Now that saturation curve, the slope of the saturation curve uh, is what is called as the delta value. So delta is nothing but this the vapor pressure difference between now. So the difference in the saturated vapor pressure divided by the change in temperature is what is giving us the delta value. So delta value, if you see, change in the saturated vapor pressure will be in units of kilopascal, and change in the temperature will be in units of degree Celsius. So this slope is what is this delta term over here. Then 5N, which is this term, is the net radiation. I'll come to that net radiation term later on. So let's skip that part now. Rho is nothing but the density of dry air in kilogram per meter cube. Cp is the specific heat capacity of dry air in joules per kilogram per Kelvin. Es minus Ea is nothing but the vapor pressure deficit that we have studied in earlier classes. Ga is the boundary layer conductance, which is in meter per second. When we talk about leaf boundary layer conductance, we are talking about the boundary layer conductance in terms of micromoles per, moles per meter square per second. Here, Ga is the boundary layer conductance in meter per second. Again, del. This gamma is the psychrometric constant. You see, it is in the unit of kP by kPa by degree Celsius, and Gs is the stomatal conductance in meter per second. Now, this rho Cp, now if you see here, if we take this term, if you take this term to the denominator, we will get the equation will become like this. E is equal to this lambda will come here, and this denominator will be multiplied by the lambda value. Now, again, some changes are required in this equation. So this is the general equation of this is the Penman-Monteith equation. Penman-Monteith equation is giving us the latent heat flux in watt per meter square. But in order to calculate the transpiration rate, we have to convert this latent heat work into transpiration rate. We have to take this latent heat of vaporization to the denominator. Now, when we take this to the denominator, and in the numerator, if you multiply and divide by lambda, we will get the term. So this lambda is multiplied and divided by in this numerator. We can see that particularly for this term. So this term we are multiplying and dividing by lambda. And this lambda stays here in the numerator, and this lambda, if we divide it by this rho Cp by lambda, this entire term is called the psychrometric constant. So the psychrometric constant that is coming in the denominator is the product of the specific heat capacity of dry air into the density of dry air by the latent heat of vaporization of air, and it is also a function of temperature. So if we have the density of dry air, if we have the specific heat capacity of dry air, which is 1010 joules per kilogram per degree Celsius, of joules per kilogram per Kelvin, also it is the same value. And density of dry air is something around 1.2 kilogram per meter cube. And latent heat of vaporization you can calculate with this equation. Even this also you can calculate it with this equation. Then you will get the psychrometric constant. So then instead of this rho Cp by lambda in this equation, we multiply this gamma into Es minus Ea by Ga into lambda by this equation. So this is the final equation that we use for finding out transpiration in plants when the weather data is available to us. So now what term is left here is phi n. Phi n is nothing but net radiation. So what is net radiation is? It is the radiation that the plant gets after we take in all the incoming and outgoing radiations. Whatever radiation is left, the short wave and long wave radiation is what is giving us the net radiation. So we had studied that in the energy balance of a leaf, the energy that is coming in is equal to the energy that is going out plus the stored energy. Now, energy that is coming in is the incoming radiation. Energy that is going out is the outgoing radiation plus sensible heat plus latent heat plus whatever is stored in the leaf during photosynthesis. Now, energy that is coming in, incoming radiation can be the short wave radiations as well as the long wave radiations. And energy that is going out also, there will be some amount of, no, this short wave radiations won't go out. There will be some long wave radiations that are going out plus the sensible heat plus the latent heat flux and the stored energy. Now whatever energy, when we say the, so why I put SV out over here is when energy is being the direct sunlight is hitting the surface, some of the energy is reflected back. That is what is this SW out. It is not actually going inside the leaf, it is being reflected back. So even that value of shortwave radiation is taken into consideration. Now, this energy inside, long wave radiation energy that is going in, minus the shortwave radiation that is going out, minus the long wave radiation that is going out, is what is giving us the net radiation, which is nothing but this term. Net radiation is short wave in and out minus long wave, short wave minus short wave plus long wave in minus short wave minus long wave out. So we can write this net radiation is equal to the sensible heat flux plus latent heat flux plus stored energy. And now we know the sensible heat flux is given by this equation. This is H. This is latent heat flux. We know long wave radiation that is emitted out is given by the black body equation, and the incoming short wave radiation is I. So this is how you will compute the energy balance of a leaf. So first what we do is, first we'll calculate the long wave radiation loss, which is given by epsilon sigma TL to the power 4. Here epsilon is given as 0.97. So 0.97 into 5.67 into 10 to the power minus 8 by 303 Kelvin to the power 4. So here we'll get 463.6 watt per meter square, which is I think the, okay. Now this is the loss, long wave radiation loss. I is the incoming radiation. Now next we'll calculate the sensible heat flux or sensible heat loss. So that rho value is 1.2, Cp value is 1005, and TL minus TA is 0.01 because, sorry, not 0.01, it is, sorry, 0.01 is the boundary layer conductance into 303 minus 298, which is equal to around 345. So multiplying all of this, we will get 60.3 watt per meter square. Now, this is also heat loss, and the only incoming heat in is incoming radiation on the leaf, which is 600 watt per meter square. So 600 minus 463 minus 60 minus that, we should not forget to minus the stored energy also, will give around 46.1 watt per meter square, which is the right answer. Anamta, your answer is right. I think Harita, you got the terms fixed. So this is the whenever you whenever you do the energy balance equation, the only radiation that is incoming is probably most of the time it is going to be the short wave radiation, and long wave radiation is going to be the outgoing radiation. Unless and until they specify that this long wave radiation is entering the system, you don't have to consider the long wave radiation as something that is going into the system. So we know that there are small amounts of long wave radiation that is absorbed by the plant, but until and unless you are specifically it is specifically mentioned that this is the long wave radiation which is going into the leaf, you just need to consider the solar radiation as the input, and the output will be sensible heat, latent heat, long wave radiation, and stored energy. Now in this question, I've given the latent heat of vaporization, and I've given the um, latent heat flux. What you require to do is convert it into evapotranspiration in millimeter per day. You can make an attempt at the question. And so here we have been given the data latent heat, which is lambda into E 50 watt per meter square. Latent heat of vaporization is 2.45 megajoules per kilogram. So if I convert it to joules per kilogram, I get 2.45 into 10 to the power 6 joules per kilogram, and density of water is 1000 kilogram. Now, in order to estimate the transpiration rate, I have to bring the lambda value to the denominator. So divide 50 by 2.45, which will give me this answer. Now, this is in units of watt per meter square divided by joules per kilogram, which is watt per meter square is 50, joules per kilogram is this one. And again, we know that 1 watt is equal to 1 joule per meter square second. 1 joule per second. So this watt becomes this one, joules per second per meter square, divided by joules per kg. This joule and this joule will get cancelled, and we will get the unit in kilogram per meter square second. Now, in order to convert this to millimeters per day, in order to convert this to millimeters per day, now the data that is given here is that so if you take the density of water for a cube, if you take a cube and if you fill it, if the density of water, what does it mean? In 1 meter cube, say if you consider a container of 1 meter cube, and if you fill it with 1000 kilograms of water, then that 1000 kilograms of water is going to be at a depth of 1 meter, or which is nothing but 1000 mm. So we want the answer in mm. So that is why I'm writing 1000 mm. So 1 kilogram what the answer that we are getting over here is 2.05 into 10 to the power minus 5 kilograms per meter square. We know that 1000 kilograms will give a depth of 1000 mm. So how much kilo? So 2.05 into 10 to the power minus 5 kilograms is going to give us what height of the water, what depth of the water, and in order to do that, we have to divide this by 1000. It is nothing but dividing this value with the density. So if you divide this energy value that you get in watt per meter square with the density of the water, finally you will get the answer in terms of meter per second. Now, meter per second, we know you can convert it into millimeter per day with by using the conversion for second to meter, and finally you will get the answer as 1.77 millimeter per day. So if you are given the units of latent heat flux in 50, this is only applicable to latent heat flux. So this is because water is involved. We know the density of water. So if you divide the latent heat flux with the density of water, or the transpiration rate that you obtain in kilogram per meter square per second by the density of water, you will get the transpiration rate in meter per second, which you can then further convert it into millimeter per day.